Hello guys, I want us to look at that question that I gave you guys in class. A frictionless pulley has the shape of a uniform solid disc of mass 2.9 kgs and radius 10 centimeters. A 1.6 kg stone is attached to a very light wire that is wrapped around the rim of the pulley and the system is released from rest. A. How far must the stone fall so that the pulley has 3.3 joules of kinetic energy? That's rotational kinetic energy, right? B says what percent of the total kinetic energy does the pulley have, right? So what are we going to do there? We are going to do this. We are told that it's going to attain this amount of rotational kinetic energy, the final rotational kinetic energy, and it's equal to what? Half omega squared times I, right? But then we know that I is going to be equal to, so we're going to have half, we know that our I is going to be equal to half mr squared, right? R, this is the moment of inertia of that solid disk, right? And then we multiply this by omega squared, but omega squared, since omega is equal to v over r, that means here we're going to put v over r. We're going to put omega is v over r, so we're going to put v over r squared there, right? So if we put v over r squared, we're going to end up getting 1 over 4 there, right? Multiplied by this mass. Remember, we're calculating the moment of inertia of the pulley, so this is actually the mass of that pulley, right, of that solid disk. So that's going to give us what? That mass we are given in the question is 2.9, so it's going to be 2.9, right? And we're going to have r squared, and then we have v squared over r squared. This r squared and that r squared are going to cancel. Remember, this is still equal to 3.3, right? So we are going to have that in the end, and then we multiply both sides by 4 and divide by 2.9. That's going to give us 3.3 times 4 over 2.9, right, equals our v squared, right? So let's see what v squared is. Remember, we will need to use v squared, not v, so we'll keep it as v squared, right? The reason is that we are dealing with kinetic energy, so we know that when we apply kinetic energy, we are going to be using v squared and not v, right? So that's going to be equal to 3.3 times 4 divided by 2.9, right? That's going to give us 4.55. So v squared is actually equal to 4.55, right? Now we write our energy equation. That's going to be K1 plus U1 equals K2 plus U2 plus the rotational kinetic energy. Because remember, the final energy that we will have will consist of the rotational kinetic energy, because at the end the pulley will rotate. So that's why we're putting it on this side. It's on the final side, so we're going to say plus the final rotational kinetic energy. I'm going to call it RKE. After that, we know that this is 0 because it's the system is starting from rest. This one, we won't make it 0, because if you look at it, you could choose either to make this 0 and keep this one. So you could choose which one you want to keep depending on your reference point. So if I choose my 0 to be where the pulley, if I'm choosing my 0 to be the point just before the stone hits the ground, which means my final point would be my what? My 0 point, my point of 0 height. So that means this would be 0, right? And I'm choosing the initial point to be my point where we have the height h, such that the stone will need to travel the height h1 that we will have here for it to actually make the pulley attain a rotational kinetic energy of 3.3 joules. So I've cancelled what needs to be cancelled. Now I can write mgh1 equals for K2, I'll write half mv. Now this is the mass of the stone, because we're looking at the kinetic energy of the stone there, right? V squared, right? Plus RKE, rotational kinetic energy, we said is 3.3, right? Now, on this equation, what we can do is that, okay, we know that this v squared is actually that velocity, because if you look at it, this is the velocity we got from there, right? From the omega. So it's actually the tangential velocity of that solid disk. And that velocity is like this there. And there it's like that, which means it's the same as the velocity of that wire. And the velocity of that wire is the same as the velocity of the stone. So we are going to end up getting what there? This m, remember, it's still the m of the stone. So that's going to give us what? That's going to give us h1 equals there 1 over 2, and this mass, which is 1.6 if I'm not mistaken. Let me check. It has to be 1.6. Yes, it's 1.6. So we're going to put 1.6, and our v squared, we have it as 4.55, right? So we're going to just write 4.55 where we have v squared, and we say plus 3.3, right? Then we divide by what? By mg, right? Which is the mass of the stone times g. So it's just 1.6 times 9.81, right? So we're going to have something like that. And if we calculate that, we're going to see that it gives us times 0.8. Then it gives us plus 3.3. Then it gives us divided by 1.6 times 9.81. Yes, that's going to give us our h1 equals 0.442. But then you will have to round off to how many significant figures there. I think it's supposed to be 2 significant figures. Let me just check what values we have. We have 3 significant figures, 3 significant figures. It's actually supposed to be 3 significant figures. So that's going to be 0.442. That's your solution there, and it's in meters. So the pulley will the stone, right? The stone will move 0.442 meters. That's your solution there. So I hope you guys understood this solution.